Hello, everybody, and welcome to today's XP Live webinar. My name is Nicole Highlander, and I'm the Marketing Manager here at XP Solutions in our Portland, Oregon office. Today's topic will discuss linking 1D and 2D domains in XP Swim and XP Storm. For those of you who may not be familiar with XP Solutions, we have a long history of providing high-performing software solutions. Our intention is to make sure that in your work, you can model with confidence. And that means that we strive to provide excellent customer service and support, and that we offer continuing education opportunities like these for engineers in our industry. Which brings us to today's presentation. Our presenter today is relatively new at XP Solutions. Venu Kandia joined XP Solutions team this year as our new Senior Water Resources Engineer in our Client Services Department. He's a very friendly voice who will be supporting you in your work with XP Swim and other XP products. He has 12 years of water resources industry experience, including that as an engineering consultant and in public utility. His pertinent experience here is in modeling, planning, and design. Thank you for joining us today, and thank you, Venu. Would you like to take it away?
Nicole, thank you for the introduction. Everybody, welcome to the tutorial webinar. So a quick overview of the topics which I'll be touching on today. Initially, I'll be looking at an introduction to 1D, 2D modeling. Then I'll be looking at setup and best practices for connecting 1D and 2D domains. Looking at some of the common errors that occur when we connect 1D and 2D domains and how you can troubleshoot those. And lastly, what are the functionalities we have within the software to look at the flows which are being exchanged between the 1D and 2D domains. So let me jump right in. A quick intro. So looking at the one-dimensional models. So typically you can look at these, and these are the link and node type models. And I'm showing two examples here. One is we are looking at a model of a river channel, and then on this right-hand side, we're looking at an underground buried pipe system that can be either a storm drain system or a sewer system or a combined sewer system. So what are the main features? We have nodes and links. The link has a certain cross-section, and the assumption is that the cross-section is uniform for the full reach itself. So going from node to node, we can define the cross-section. So if you're looking at this river itself, we can define the channel cross-section. If you want to use a one-dimensional model to understand what's happening in the floodplain, then we'll go and digitize it and have a definition of the floodplain. One of the drawbacks is the cross-section has to be uniform for the whole length itself. And then we go and solve the equations, and we solve the continuity equations and momentum equations. And what we end up getting is we get a grade line at the nodes itself, and then we get flows, velocity, and then flow area through each of the links. What are the advantages of one-dimensional modeling? They're relatively easy to build. You can model large areas, and they require low computational effort. This is compared to 2D models. Once again, and their theory is less complicated than two-dimensional modeling. They've been around for a long time, so they're well accepted within the engineering community. The biggest disadvantage we have is that the assumption of you can only have one-dimensional flow. Oftentimes, you have situations where flow is basically, let's say, overtopping the channel bank itself, or you have a storm drain pipeline which is surcharged, and you have overflows where you have flows coming into the urban area. That cannot be properly represented within a one-dimensional model because those are essentially two-dimensional flows. So within a 1D model, if you want to try and get an estimate of 2D flows, you need to be aware ahead of time potentially where flows can occur, and you need to cut cross-sections so that you can, in some ways, kind of interpolate from the results what 2D flow regimes occur. So we can switch over, and then we have the other type of modeling, two-dimensional model. In XP, we use the concept of grids, and two-dimensional modeling uses a set of uniform grids. The grids contain the information on the topography, so we have elevation information. In addition, they control the hydraulic parameters, so we have the land use data, roughness, and any other hydraulic parameters needed to compute the two-dimensional flow. The momentum and continuity equations are solved at the grids. And what we end up getting is the water surface level at each grid, at each time point, and then the flow going from each grid to adjacent grids. The advantages of two-dimensional modeling, it's relatively easy to build a model of 2D flows. The main thing that we need is a good topo map, a surface map. a lot of the things that we want to look at when we are looking at two-dimensional flows, so flood flow storage effects and then indentation maps, those are created directly from the two-dimensional model. Whereas in a 1D model, you only get the water surface elevation at a cross section, and you need to extrapolate to figure out what's happening for storage effects and inundation. These are done automatically in the two-dimensional models. So in some ways, you can say there's less engineering judgment required using a 2D models. But there are some disadvantages to using a 2D model. You need good, precise, and dense survey data. The quality of your data, survey data, basically your topo information, that will dictate how accurate your two-dimensional flow results are. It requires more computational power and time than is required for a one-dimensional model. And then there are two other things that we need to look at. It's basically, it becomes relatively difficult to model very large areas with a small cell size. And then there's also a trade-off in the accuracy and the representation of the cell size. I'll get more to these 2 points in my next slide. And 2D modeling is a relatively new approach. It's maybe been around the last 15, 20 years in the engineering community. So it is not as well accepted as the 1D modeling. And it's still, you can say it's in the phase of development and being accepted by the community. So one big issue we have in two-dimensional model is the concept of discretization. If you take a look at this channel cross-section, what is shown in green is the actual channel cross-section. In this particular example, we are assuming we have a grid cell size of 5 feet. So the way the channel gets represented in the 2D model is shown in the red line. Let's say we are looking at low flow conditions and everything. The flows that we are estimated and simulated in the 2D model might not be accurate because we don't have that. It's a very coarse representation of the natural channel itself. So what can we do in such situations? One thing is maybe go and use a smaller grid size. The only issue we have is the smaller the grid size, the more the computational requirements are. So there's a big trade-off between the cell size itself and the computational requirements. Let's say if you use the grid size half of this size, the computational power goes up 8-fold. So that is one big issue in 2D modeling. So there's a whole concept. We know 1D models are good for certain applications, and then 2D models are better for other applications. So if you're looking at situations where we can have both a combination of one-dimensional flow and two-dimensional flows, it makes sense to couple the models together and use each approach for the modeling that is best suited for. So we can use a 1D model to model any underground pipe flows, so storm drain systems and sewers and culverts and any channel flow. And then anytime we have flows going overtopping the banks of the channel and going to the floodplain, go and use a 2D model for that particular domain. And the same thing, if the flows from the buried pipeline and they're reaching the surface itself, you have some street flooding, go and use model that in 2D. And if you have wide water courses, then you can model those in 2D. Before I go on to the next slide, I think now is a good stopping point, and we'll do a quick survey and try and get a feel from the audience on what sort of applications they do 2D modeling. I'll ask Nicole to take over and do the poll.
Absolutely. So you can see on your screen now what are typical applications for which you currently use or plan to use 2D modeling. The options are floodplains, urban areas, so if you have a lot of underground systems that you have to deal with, maybe coastal areas, wetlands, or dam break. All right, I'll go ahead and close that. Can you see that, Venu?
Yeah, I can see that. So the results are basically what we're saying, 90% of the audience is using 2D modeling to look at floodplains. 80% is looking at urban areas. And then we have 30% are looking at dam breaks, 20% at wetlands, and 10% in coastal areas. It works out pretty good because I'll be focusing on the two areas where most of the audience is interested in. So looking at floodplains in urban areas and how we can combine 1D and 2D modeling in both of those application areas. The main takeaway point from this is that 1D, 2D model is advanced to the point that there's a lot of flexibility in how it can be applied. So if you look at this particular, we are looking at this is the extent of the 2D modeling itself. You can go and embed 1D models within your 2D domain spatially in multiple locations. You can have multiple 1D models all connected to each other. So there's a lot of flexibility in using a 1D, 2D model. For example, within a small area, we can go and model a culvert. So this is an isolated area itself. And then if you look, we can call this a channel or a river bed running through it. And then we do have a storm drain system. Each one is an independent 1D model embedded within the larger 2D model, and those can be connected. Now, looking at the applications that we want to focus on, the first one that we're looking at is modeling a riverbed flowing through a floodplain itself. Let me jump over to the cross section. As long as the flows are within the channel itself, we can model that within 1D. It's well suited for 1D applications. Anytime we start getting flows over the top of the bank itself, and then it starts going to the floodplain itself, we're going to do the 2D modeling. So basically, along the length of the river reach itself will be 1D model. Once you top the bank itself, then we're going to start using 2D modeling application. If we start looking at urban applications, what we have here is a storm drain system within an urban area. As long as the flows are within the pipe itself, we can go and use 1D modeling. That's the most suited. So anytime the flows are within the pipe system, it's 1D. Once you start getting flows to the surface itself, we switch over and then we hang the 2D modeling. So surface flows will be modeled in 2D. So I'll go ahead and jump into setup and best practices for 1D, 2D modeling. 1D, 2D modeling are fairly complex. So it's highly recommended that we go ahead and develop the 1D component of the model itself. It's easier to build itself, it's easier to debug, and once we have a working model, then we can go and combine both of them together. If we start working on both the 1D and 2D models simultaneously, it becomes somewhat hard to figure out where the errors are, what are the boundary conditions, what's missing. So go ahead and develop the 1D model, get that working, and then we can go ahead and combine that with the 2D model. The next thing we want to do is we need to have a clear understanding which components do we want to be modeled in 1D. Where is the flow regime more acting as a 1D flow and where is it acting as a 2D flow? So within the study area, what can be best suited for 1D modeling? What is best suited for 2D models? What are the linkages? Where is flow switching over from, let's say, one-dimensional flow to two-dimensional flow? A couple of things to keep in mind. Let's say we are modeling a channel itself. If the channel is being modeled as a 1D, we want to make sure that the extent of the channel is removed from the 2D surface. We don't want to duplicate the conveyance area and then storage areas. So we need to make sure that happens. Another example might be modeling a pond, and we model the pond as a 1D node. We need to make sure that the footprint of the pond is removed from the 2D model. Once again, we don't want to be double counting the storage area within the pond. So once we have the 1D model developed and then a good understanding of the 1D and 2D limits and how they're going to be connected, we can go and start developing our 2D model. So 2D model construction within XP, the very first thing is we need to define the 2D grid and then the surface. So this is the limits of the area which is going to be modeled in 2D. Go ahead and divide that and you break it down into regular shaped grid sizes. We need to import in a topo which has the surface information. So basically the elevation information that gets translated to the grids, and that will be used for the two-dimensional flow computations. The next thing is any area which has already been built and is being shown in the 1D model needs to be excluded from the 2D model. So we define a 2D inactive area. The next thing that we do is we develop the connections between the 1D model and the 2D model. So I'll be looking at two examples. When we have a channel, what are the connection types we can use to connect the channel to a 2D model? And then in an urban application, when we have a storm drain system, how can we connect a manhole to a 2D system? The next thing is, this is for the 2D grids itself. We need to define the land use. In land use, primarily what we are looking at is the friction factor, any other hydraulic parameters, which will define the flow equations. Define the boundary conditions for the model. Go ahead and set the job control, and then the model is ready to go. So I'll be looking at two applications, and the first application is looking at how you can connect a channel defined in 1D to a 1D 2D model. There's a lot of information on the screen, and I'll just walk through them one by one. So we have modeled a river in 1D. So what we have is basically the node. Then we have one river reach, which is shown by this link over here, and then the downstream node. We'll be modeling flows within the river channel within 1D, and anytime then the flow exceeds the top of bank, then that's going to go into the 2D model. So the first thing we want to do is we want to clearly distinguish where are the flow elements going to be within the 1D model and where are they going to be within the 2D model. So in this particular area, we know where the top of bank is. So the top of bank will serve to delineate two areas. One is going to be what is inactive within the 2D areas. So everything within the top of bank is going to be channel flow within this limits. Once you exceed the bank level, then that's going to be 2D flow. So this will delineate where the flows are switching from 1D to 2D. So this becomes an inactive area in that we don't model that within the 2D. And it's also interface between the 1D model and the 2D model. The second thing we have is we have the 1D model. It's going to go and it's going to calculate the grade lines and the nodes themselves. That information needs to be conveyed over to the 2D model. We use the concept of a 1D 2D connection line to pass the information from the node, which is calculated in the one-dimensional model, to the two-dimensional model. So at each time step, any head which is calculated in the node will be transferred over to this. So what we have in this system is we transfer a water level surface or head both at the downstream node and then upstream node. And then the head value gets interpolated along the interface line, and then that's transferred to the cells adjacent. So let me switch over to the model itself, and I'll show how this gets done within XP Swim. So I'm within XP Swim, and what we have here is I've already built the model for the river channel itself, and it's a 1D model. So we have node and then the link representations. So I'm looking at 1 node, 2 node, 3 node. The river is coming in and we're crossing a road embankment. So we have a culvert running underneath the road itself. For the river itself, I defined the cross section, and that's shown by this blue line. So this is essentially a 1D model. I'll go and turn on the grids. And this 1D model is sitting on a 2D model. So the first thing that we want to do is basically this area is being modeled within the 1D model. So we don't want to duplicate that for, and we don't want that to be modeled in the 2D model. So the first thing is we make this area which is being modeled in the 1D model inactive within the 2D model. To do that, we go to this icon, the 2D model. We'll be creating a new layer, and that's going to be an inactive area. So that's an inactive area within the two-dimensional model. Go ahead and give it an appropriate name. I'll just call it inactive. The inactive area is a polygon type. So we'll go to the right-hand side and we'll click on this icon, which is create a polygon. We have a fairly good topo which shows us where the top of bank is. So we'll be delineating the polygon along the top of bank itself. I'll just go ahead and follow, click on it, and then I can just follow this. In the ideal situation, we will pay proper attention and delineate it as accurately as possible. For sake of time, I'll just do a rough approximation. Couple of things to keep in mind when you're delineating the polygon. Try and keep the length of the channel itself fairly constant. So the width has to be fairly constant for the whole length. So I'll delineate one side, and then I'll jump over to the other side and I'll delineate the other side along the top of the bank. So the area which I'm delineating it's done once I go and double click it. So the area is shown in hatched, and this will not be modeled within the 2D area. It's only going to be modeled within the 1D area. The next thing that we want to do is we need to create an interface line. So it's basically the interface between the one-dimensional modeling domain and the two-dimensional modeling domain. So once again, you can go to 2D model layers. We'll be adding a new layer, and this is called the 1D 2D interface. Give it an appropriate name. The 1D 2D interface is going to be a polyline. So go ahead and click on the polyline create over here. We'll go ahead and turn on the snap feature. And then we have this feature within XP Swim and XP Storm. Anytime you have drawn a polygon, and if you want to delineate a polyline around it, you can just click on one vertex and then click on the shift button, and then if you move to another vertex, it draws a polygon all the way around the existing polygon. So it saves you the effort of having to go back and digitize along the same extent itself. So just double click here, and we have defined the interface itself. So the next thing is I'll go ahead and I'll turn off the hatching for the inactive area just to make things clear. So we have the one-dimensional model, and then we have the interface line between the 1D and the 2D models. We want to pass on information from the one-dimensional model to the 2D model. The interface is where the information is transferred over. We still don't have the information which has been computed in the 1D, 2D model. So to pass the information from the 1D model to the interface line, we'll use what are called 1D, 2D connections. Those are, again, once again, within the 2D model, we'll be adding a new layer. And those are the 1D, 2D connections. So go ahead and select the 1D, 2D connections, and that's just a polyline. So I'll be creating a polyline. All we need to do is snap on the manhole. So any value calculated in the manhole will be transferred to this vertex. So we want to be passing the information from this manhole to this vertex. So this information will go to one bank, and the same thing, information from this manhole has to be passed over to the next bank. So I'll go ahead and click over here. Do the same thing for each manhole from here to this vertex. Go from here to that vertex. And the same thing, we can either click on the interface and go to the manhole, or we can go from manhole to interface. So I'll do the same thing on the other side. So we've defined our inactive area. We've defined the interface itself, and we defined the connections itself. The last thing that we need to do is make sure that information from the manholes is being passed on to the 2D model. To do that, go to the nodes itself, select the node, edit the data, and come over to this option over here. And what we want to do is we want to link the invert to the 2D model itself. So make sure that this option is selected. That needs to be done for all the nodes, so we can do that. We have one feature. Let's say within a dialog box you already made the changes and you already connected link invert to 2D. You can go, so I'll go back to the very first one. I've already done this process. You can just click on the copy button. Click on the copy button, go ahead and click on this. So one feature which has been done, click on OK. Choose the other two locations where you want to do exactly the same edits. Just do a right click and you can do a paste. What that does is any commands that you had copied get transferred over to any others where the information is pasted to. So you can see that it has automatically converted that information over here. So those are the 4 steps, essential steps that need to be done to link your 1D channel to a 2D domain. The next thing that I want to look at is how do you connect manholes? Let's say you have a buried pipe system and you want to connect the manholes in 1D to 2D. This is a much simpler process than connecting channels in 1D to 2D. All you will have to do is go and edit the manholes. Within that, there's an option where you can link the spill crest to 2D. So go ahead and make sure that option is selected. The second thing that you want to choose is we have this option 2D inflow capture. Go ahead and make sure that option is also selected. As soon as you do that, it gives you this equation. What this option is doing is it determines and it lets you choose how flows from the 2D surface can enter the manhole itself. So you can go ahead and give an equation. What is the unit flow of area based on the depth you have within the 2D cell raised to a certain power? This is the default equation, but you can go ahead and change to whatever is most applicable for your particular situation. I'll go ahead and show how this is done within the model. So I'm looking at a model, and let me highlight all the modes. So we're looking at a model. Basically, it's a 1D, 2D model. We have a stone drain system, and then it's connected to a 2D grids over here. Go ahead and click on a certain manhole. We can just do edit data. So to have this manhole connected to the 2D cell, all we can do is, it's already selected, link the spill crest to 2D. And then the second option I had where we define how flows from the 2D surface are entering the spill crest or the rim is to go ahead and click the 2D inflow capture. It gives you the option, and then you can define the equation for inflow into the manhole. So some of the common errors that we often run into when we are linking 1D and 2D models and how we can troubleshoot them. So what are the things that we need to watch out when we are modeling culverts? Assume that we have modeled the culvert as a 1D element. So flow through the culvert is going to be defined based on the water surface elevation at either end. Assume that the culvert is in 1D and then the remaining portion of the models are in 2D. The model is going to use the water surface elevation in the cells on the upstream end and the downstream end to determine the gradient, and that is going to determine how much flows you're getting going through the culvert. So in a sense, the 1D element is going to act, and there's going to be, you can call it a sink and then a source, so that we are driving gradient, and then there'll be a sink and source. You'll be getting some flows coming from one 2D cell going to the other 2D cell. So the main thing to watch out for is you have a 2D cells defined at a certain size. What is the size of the culvert that you're trying to model in relation to the size of the 2D cell? If the culvert is smaller than a typical 2D cell, you can go ahead and assume that you can just have one point on either side. So you can get flows coming from one 2D cell and then discharging to another 2D cell. Let's say you have a relatively small grid cell size and then the culvert is it's a multiple sizes of the grid cell size. Then you want to make sure that you're getting flows from multiple grid cells and transferring them to multiple grid cells. I'll switch over to the model and see how this can be modeled within XP. I'll go back to the same example model that I was looking at before. So this is where I have model culvert, and then I'll move over to the downstream portion of the culvert. I'm using 5 meter grids, 5 meter square grid cell sizes. So if this culvert is 5 meters or less, the way we have it modeled right now is accurate. And then basically we're coming and we're discharging to a certain cell itself. Now in the instance, let's say this is a 10 meter culvert, we want flows coming out and then you won't be discharging to a single cell and we want it discharging to multiple cells. So what we will do, we'll go back to the 2D model. We'll be adding a new layer and then we're adding a 1D, 2D interface. I'll go ahead and call it culvert for this example. Go ahead and select that 1D, 2D interface, and then it's a polyline. Assume that the flows coming out of this are going to be discharged to these two cells in the 2D domain. Go ahead and draw an interface line which covers both of those. Double click on them. And the next thing I want to do is we want to go ahead and connect our 1D model to this 2D interface line. So any flows coming through this 1D link will be spread among these two cells. So here the flows discharging to both cells. So the next thing that we need to do is we need to connect the 1D element to the 2D interface. So go ahead and right click. Go ahead and right click over here, adding a new layer. And this is once again a 1D, 2D connection. I'll just call that a culvert. Go ahead and select that, and that's a polyline type. Select on the polyline. So you can just click on the manhole itself, and then you can click to any one end of the 1D, 2D interface that we created for the culvert. So we're done with culverts. And another thing, when we are modeling our channels in 1D, one thing that we need to watch out for is the frequency of cross sections. In this particular example, we have cross sections which have been shown in the 1D model, and we have them too frequently. The problem we have is when you have cross sections very frequent and then connected to a 2D model, it can often lead to model instabilities. So a rule of thumb, it's recommended that basically when you're coupling a 1D model to a 2D model, use a spacing of maybe having a cross section spaced every 5 to 20 cells. On the flip side, you don't want to have the cross section spaced too far apart. If they are too far apart, then you won't be getting a proper linkage between the 1D and the 2D models. And so there won't be a good representation of the head is changing between the 1D and the 2D models. Next thing that we want to look at is we have a model which has been defined in 1D. And one thing that we need to remember is when we define a 1D model, we are defining head at both locations. We have node at the upstream location and node at the downstream location. Then we are defining a link. And then the link, we have a channel cross section. So in this particular example, what we have is we defined a spill crest for the manhole. If the spill crest for the manhole is defined at too low of an elevation, what's going to happen is anytime if we're under a condition where we have 2D flooding, if the 2D flooding level is actually much higher than what we define as the spill crest, we'll actually be getting flows from the 2D flood over here. But the way the XP works is within the 1D domain, once you start getting flows over the spill crest, either that will go into storage or this system is going to start acting as a pressurized condition. So we'll be inaccurately representing what's happening under a flooding condition. So how do you go about fixing this? Before modeling, it's good to have a understanding of maybe the highest expected flow levels within the 2D model itself. Go ahead and define the rim or the spill crest for your manhole such that it will always be at a level which is the maximum level that you can expect the 2D flooding to occur at. And the next thing that you want to turn in is turn on the concept of the vertical walls. When you're defining your channel, you're defining the channel itself, and it's just going to go from top of bed to top of bed. What happens is, if you don't have any flows defined where it starts spilling over, if you use the concept of vertical wall, it defines a vertical wall starting from the both edges of the banks itself, and all one-dimensional flows will be retained within this surface as long as you are within the spill crest elevation. So we end up confining the 1D flows to over here, and then anything overtopping will be in 2D flows. To turn on the vertical walls, that is a feature which we have within the configuration parameters. So we'll go to configuration parameters, and then we use this special parameter vertical walls. Another thing that we need to notice when we are looking at 1D, 2D models is, so you have the cross-section which has been defined within the 1D, 2D model, and then we have the 2D domain. The 2D domain is going to use a topo, and it's going to get up a cell surface elevation. Oftentimes you might end up with there's going to be a discontinuity in the elevation at the top of bank and the cell elevation itself. In this particular example, if you're looking at the channel itself, we have the channel, top of channel elevation in the 1D model. It's 176 on one side and then 175.8 on the other side. And then if you look at the 2D cell elevation, it's only 174.31 on this side, 174.5. So there's about 1 to 2 feet drop between what's being modeled in 1D versus what's being modeled in 2D. This is bound to happen based on the grid cell sizing you have. So we do have a tool within XP software which can help you detect this issue and also fix it. So how do we go about using that feature? So once again, I'm looking at it's a similar example to the one which I had worked on before. We are looking at a channel over here. The channel is modeled in 1D, and then we have a 1D 2D interface, and it's connected to a 2D model. So that's a great extent for a 2D model. I'll go and turn that over. If we select the 1D 2D interface, go ahead and select that, and then if you do right click, you can go ahead and display a profile for the 1D 2D interface. This window pops up, and then it shows you a profile of the 1D 2D interface. So there are a couple of pieces of information in here. Shown in green is the interpolated bank elevation. So this is based on what has been used for the 1D model itself. You have defined nodes, and then you define the cross-section, and you get some elevation. So you have bank elevation. So this is what we have within the 1D, 2D model. Shown in red is the grid elevations. This is the information which is being used by the 2D model itself. So if you look at along this length of the bank itself, the 2D model is, we can say it's fairly closely matching what we have within the 1D model itself. Once we switch over and then we come to this side of the bank itself, we see that the grids in the 2D cells are much lower than what we have within the 1D model itself. So we do have the feature where you can go and automatically correct that. So you will create a thick ridge line. What this does is it creates a ridge line which will automatically raise the 2D cell elevations so that they more closely match what we have defined for the bank elevation in the 1D model. All you will have to do is go and click on this option, create a thick ridge line. So it's going to raise the 2D surface bank to the bank itself. I clicked on it and the process has been done. The new bank which has been raised is right underneath the existing bank elevation. It doesn't show up. Let me go to the graphical view and I'll show you where that it's defined. So go and click on OK. So this is where we have the interface line itself. I'll turn that off for the time being. I'll go and show my topo layers. If you look under the topo layers, by going through that process, we've generated a set of ridge lines. Go ahead and select the ridge line, edit the ridge line. So if you look at the ridge line, this was the original elevation information along the ridge line, and this is what was being used by the 2D model. Based on what we were using within the 1D model, this was what the top of bank elevations were. So we've adjusted it, and the ridge line has been put in here so that instead of using what was originally digitized, this is what is being used within the 2D model itself. So what this does is, for the grids along the interface line itself, those have been adjusted so that there's no discontinuity, sharp discontinuity between the topper surface that we have modeled within the 1D and the 2D model. They are more closely matching. So this is, you're able to get a better flow moving from the 1D to the 2D model and less chances of getting model instability. Now, if you look at manholes, one of the errors that we can have when we are connecting a manhole in 1D to a 2D model is this situation where the 2D surface is much higher than the top of the manhole, than the rim or the spill crest of the manhole itself. This can be fixed automatically within XPSWIM. We have the option, we can go to 2D job controls, and there's a feature where it'll go and it'll go and lower the 2D cell so that it matches the elevation we have for the rim itself. We don't want to have the situation because basically there's a discontinuity and any flows that enter this area will get lost and it will lead to model errors. So we have a feature built in within the model which is check for this condition and fix it. We can have this other condition which can also sometimes occur where the top of the manhole, the rim, is higher than the 2D surface elevation. What's going to happen is basically the manhole will act as a smokestack. Any water surface that you have within the 2D has to actually raise up to this length before it can go into the manhole itself. And the same thing, any flows coming out of the manhole will be dropping over onto the surface. This condition can potentially occur in real life, so we don't correct for it automatically. But there are tools which you have within the software where you can go and you can look and you can go and lower the manhole rims to the grade itself using this one tool, or you can just go in and fix it manually. I'll switch over to the model and show how these can be done. So the very first condition that we were looking at is we can go to configuration, job control, 2D model settings. Under 2D model settings, we have this level condition over here. Go to level, and then we have this condition. If the 2D cell at a 1D node connection is above the node 1D spill crest, you can just go and click on this. So it'll automatically lower the 2D cell to match the spill crest elevation. So that is one option that you can choose. The second option you can go is you can just go to tools, and then you can just do generate the ground elevations from 10. If you go and do this, no matter what elevations you have within the 1D model, it will go and readjust those elevations to match the 10. So that's more likely closely to match what you have within the 2D model. So we have the 1D, 2D models, and one thing we want to understand is what are the flows, how are flows being exchanged between the 1D and the 2D models. So there are a couple of locations where this information is reported. The first thing is if you look within the 1D log, within 1D log we have a table E19. It's a summary table of the inflows and outflows at each junction. So in table E19, information is categorized by junction itself, and then for each junction, we have the total inflow which is coming from the 2D layer. So this is going to be for the total duration of the model simulation. This is table E19. And then if you go to table E20, we have the other information. How much flow is being sent from any particular junction to the 2D cell. Once again, this is summarized for the total duration of the simulation. The next thing is maybe we don't want the total information and we want actual hydrographs. So we do have that information that also can be generated, and it's generated as a check file. So we would have to go to 2D job control. Within 2D job controls, you'll have to go and select this option, enable and produce check files. Once that is done, you go to the advanced settings, and that is going to be in this dialog box over here. In advanced settings, you'll go and click on insert and you'll get a new field. You need to key in this parameter, or write X1D check files, and then you need to turn on the parameter to on. So what this does is basically it goes through the simulation itself and it creates two CSV files which generate hydrographs on the flows which are going from the node from the 1D model to the 2D domain, and also flows coming from the 2D domain back into the 1D model. The data which is generated is of this format. So this, I had already run the model ahead of time, and then this is we're getting a report on flows which are coming from the 2D into the 1D model itself. It goes through and lists the different nodes which are connected to the 2D model. These are the simulation time steps, and if you scroll down, we basically get a hydrograph, how much flows are coming from the 2D model into the 1D. So we get two sets of hydrographs, flows from the 1D model to the 2D, and flows from the 1D, 2D back to the 1D. So a summary of the information which I covered, coupling 1D, 2D models, it offers a good approach of modeling systems where we know we have a combination of both 1D and 2D flows. We can use the strengths of each approach, and it's computationally efficient. We can have multiple domains. It's spatially discrete, and we can look at it. We need to have a good understanding before developing 1D, 2D models, which parts of the system are best represented in the 1D model, and which of those are represented in a 2D model. So understand where the system breaks up, what are the connections, and what are the linkages. A couple of things we need to be aware is, as soon as you start doing a 2D model, you do start doing some discretization. So as far as elevations and hydraulic characteristics, as soon as you break information which is maybe continuous in nature into discrete, maybe certain grid sizes, how is it being changed? And you need to be aware of that. For example, if you have a channel which is less than the grid cell size, the channel is going to be represented as certain grid size. Is that going to give a high hydraulic representation? If not, maybe use that as a 1D, or maybe use a smaller grid cell size. Then the next thing that we need to be aware of is the connections and the boundaries we have between the 1D and the 2D. Go ahead and run the model. Go ahead and double check those locations. Those locations are prone to maybe inaccuracies and everything. Make sure that the flows are actually being transferred correctly, and what you have represented in the model is actually what you need. So that those are locations where once the model has been built, go ahead and double check. A lot of times instabilities occur in the connections between the 1D and the 2D models due to the disconnect, maybe in the size of information that is being passed over, or the cell sizes don't mismatch. One of the questions we had is, when modeling a channel, why do you select the option of linking the invert to 2D and not the spill to 2D? So basically what we want to have is, when you have the channel, the flow is going to be start building up all the way from the invert itself and then going all the way to the rim itself. And the way you have the 2D surface defined, maybe the rim elevation in the 1D model might be somewhat lower, or there'll be a mismatch and everything. So you won't have the ability of the flows, not only when it exceeds the rim, being transferred to the 2D model when you have modeling a channel, whereas when you have a manhole, only when the flows overtop the rim are they being transferred to the 2D. So for a channel, best practices is basically you are connecting the invert elevation, and based on what you have defined for the 2D grid itself, until the hydraulic rear line exceeds the level in the 2D surface, you won't get water overtopping. But it's just a best practice when you're linking a channel to a 2D surface to go ahead and link the invert itself. There was another question asking about flow balance, and I kind of touched on it at the very end. So you can go to the 1D output log, and tables E19 and E20, they offer a summary. Another thing is you can go and create the check file, and that will create basically hydrographs at all the different locations, and then you can go node by node and you can get a good understanding of flows which are being conveyed from the 1D domain to the 2D domain. I think that about addresses most of the questions. And
there was one other question I think that you'd be able to answer it pretty quickly. Does the program have a hydrology component that includes green amps for losses?
Yes, it does have. I didn't touch on it, and there's a whole component where we do have various hydrology methods, and that is included. And there are about 9 or 10 different hydrology methods. And if you want to send us an email independently, we can send you a link of all the different hydrologic methods we have within the program itself.
Before we go, a question that was asked at the last webinar earlier today was, is XP Swim and XP2D FEMA approved for flood for NFIP submission? And yes, XP Swim and XP Storm are both FEMA approved for 1D and 2D modeling. Also, it has been pretty rigorously tested by the UK Environment Agency with excellent results compared to other programs. So yes, XP Swim can definitely help you in those situations. And with that, I think that's all the questions that we have. Thank you so much, everybody, for joining us today and for getting this information. If you have any questions, our contact information is currently on the screen. You can contact us, or you can contact Venu directly, or you can always go through our support portal to get your questions answered. Thank you, Venu, for your time today and for the information that you've presented.
I'd like to also thank everybody in the audience, and any questions, feel free to submit questions to us on the support portal or just get in contact with us. We're glad to help you in any way we can. Thank you again for your time.